Okay, thank you, Wolfgang, and thanks, Wolfgang, Katarina, and Akash for organizing this really nice workshop, and for the kind invitation for this talk. Yeah, it's actually my first time that I'm really following a fully such a workshop. And if you go to the coffee breaks, I advise you all actually to do that. You almost get like a conference feeling, because you tend to meet people for a longer time than just a talk. And yeah, thanks also to organize this meeting in such a wonderful place, as you can see in the picture. You could have organized the weather a bit better. It's raining outside, but yeah. So I will tell about work that we reviewed recently in these two papers. And I make a disclaimer in the beginning. We hope to have been complete in the referencing in the reviews, but the talk will not be complete in that sense. So, but if we didn't cite your important work, please, in the reviews, please let me know. So the review and sort of many parts of the work that I'm telling you about have been were written together with these three people: Seba Spesere, Michal Silaev, and Pauli Virtanen, and many people have contributed to sort of my part of the research in this field. Okay, I start from very basics, and sorry for a very layman introduction. So the whole workshop is about a combination of superconductivity and magnetism, and as I believe all of us know, these are believed to be the ground state of most metals at a low temperature, and they describe a procession system. Yeah, so in this talk, for me, magnetism means two things: an exchange field which splits the spins, sort of the energies of different spin bands, and then the spin polarization that results from this spin splitting. So spin polarization of observables. So for example, density of states could be written in terms of such a spin polarization. Actual magnetic field in magnet is not really relevant here. I will mostly disregard spin orbit coupling and in this talk. But that will also actually lead to, of course, many interesting phenomena. Superconductivity is described by another parameter, which is the pairing amplitude, and or the pair potential that results from this pairing amplitude. Here, I will concentrate on S-wave superconductivity, but we'll discuss both singlet and triplet pairing. And this pairing amplitude is a convex number, so gradients of the phase lead to the supercurrent, which is, of course, a distinctive feature of superconductors. But another very distinctive feature is the controllable energy gap in the dispersion, which actually will be the more important concept in this talk. So, of course the energy gap is proportional to the pairing amplitude. Yeah. And this shows in particular in the BCS density of states, which has the gap of size 2 delta and the BCS divergence. And okay, now superconductivity and magnetism, they usually don't really like each other. And as you can see from the Meissner effect picture, they even physically repel each other. So they don't usually like each other. But of course, in nanostructures, we can actually place them next to each other. And this is what I will talk about in this talk. So my idea is to bring these two, a magnet and a superconductor, together and see what happens, in particular on the superconducting side, and how this can be studied by various experiments. So this is sort of the schematics. So let's make an superconductor ferromagnet bilayer, in particular with the superconductor and ferromagnetic insulator, or you can also assume that similar effect you would also get by applying an in-plane magnetic field in the superconductor. And if the superconductor is a thin film, the orbital effect does not play a big role. What happens in these cases is that the superconducting spectrum splits in spin. there is a spin splitting, and this sort of shows up in the density of states via the spin splitting. And the detailed mechanism of how the ferromantic insulator split the spin and the sort of theory of this for finite thickness superconductors was presented in Alberto Hijano's poster yesterday. Yeah, so the point of the ferromantic insulator here is really to provide the spin splitting almost without an external field, and actually the sort of field scales that are needed in this ferromantic insulator case are usually much smaller than in the case where you do the same with an external Zeeman field. The first question to ask is that if you now apply this exchange field, what happens to superconductivity? And this was discussed already in the 1960s by several people, Chandrasekhar, Clockstone, and others. And basically what they found out was that eventually the induced exchange field kills superconductivity. So that this is the superconducting order parameter as a function of the induced exchange field. And you find out that at large exchange field, there cannot be any superconductivity. At low temperatures, the phase transition is actually a first order. So there is a regime of exchange fields where there are basically three solutions, one of them unstable, to the self-consistency equation for superconductivity. At high temperatures, then it becomes a second order phase transition, so that there is only a single valued delta. And so one interesting sort of phenomenon happening here is actually sort of in regime around here, which is this so-called Larkin-Ormschinikov full referral state, which, as far as I understand, has not been seen in this type of superconductor structures as such. So phenomena related to it have been seen in many places. Okay, the theory description of this phenomena, what we use is based on the quasi-classical technique. I explain it a little bit here. This is probably more for the experts. Not if you don't capture all the details, it doesn't really matter for the rest of the talk. But how we describe this is via so-called Usalal equation derived by Usalal in the 1970s, which describes a dirty superconductor. And this is a diffusion equation for the Green's function of the superconductor, and you can include to the description sort of superconductivity via self-energy, different relaxation terms via their self-energies, and then the spin splitting, which is the exchange field term here. And if you describe this Green's function in a Keldysh formalism, you are able to describe both the spectrum, which come from the retarded and advanced parts of the Green's function, and the state of system which come from the Keldysh part. And in the superconducting case, this retarded advanced functions, they are actually, all these functions are matrices in Nambu space, in the electron hole space, and so they consist of the let's say G and F functions. But now in my talk, I consider the case where there is the exchange field, and in this case, it's relevant to consider these G's and F's as spin matrices. Okay. Then, in addition to this Usalal equation, which describes the Green's function in a bulk, we also need to have a boundary condition to describe an interface between a superconductor and a ferromagnet. And this boundary condition then describes either spin polarized tunneling or induced exchange field from the ferromagnet. Now, what happens once you spin split the superconductor to this Green's function is that basically it obtains spin-dependent parts. So you have a spin signet part and a spin kind of triplet or sigma z part. The precise Pauli matrices that you get here depends on how you choose the so-called Nambu vector, but this is maybe the simplest way to describe it. So both G and F get this non-trivial spin dependence, And the G part describes the spin-resolved density of states, and the F part describes the F0 is the singlet pairing amplitude, and then the Fz is actually a triplet pairing amplitude. I believe the next two talks will discuss this triplet pairing a little bit more. To be consistent with the Pauli principle, an S-wave superconductor cannot as such have a triplet pairing, but what has been shown is that actually what this Fz here is actually an odd frequency triplet pairing, and that's then it's consistent with the Pauli principle. Now, in the case of only collinear magnetism and no spin-orbit interaction, you only get this one Fz part, and you can think that this is so-called m equal to 0 triplet. In the next two talks, I believe there will be also discussion of so-called long-range triplets, which contain then the other Pauli matrices. Okay, but now once you have this Prince function, you can also then study what happens to the pair potential, and this is what you get from a self-consistency equation, which in equilibrium looks like this. So you actually only couple to this singlet pair potential in a sort of typical interaction model describing singlet superconductors. Yeah, but one thing that you can do now with this Usual equation is to study this transition, paramagnetic transition driven by the exchange field a little bit sort of more in detail. And in particular, you can study, for example, how spin relaxation affects this transition. And sort of more or less what you can find is that if you have spin flip scattering, this reduces the critical field for suppressing superconductivity, whereas spin orbiting scattering increases the critical field. And this is sort of, this might be the relevant phenomenon for heavy metal superconductors. So in this case, actually the critical field for paramagnetic transition is much increased. The way to study this superconducting, the spin split superconducting state is the easiest way is by tunneling. Such tunneling experiments on spin split superconductors have been done since 1970s by Messervy and Fedro, and especially by Jagedis Moidera in several works. We heard some of them just 2 days ago. The simplest case is basically you couple just a metal via an insulator to the spin split superconductor and study the tunneling current. It can also be a ferromagnetic metal, and I will discuss in a moment what that implies. In the collinear case, basically you get just the current that depends on the densities of states of the two metals that you study, and then the difference between distribution functions on those metals. And this is so-called semiconductor picture describing this tunneling, where you can place a spin-dependent density of states on the right-hand side of the superconductor and study the different processes. We recently studied sort of the most general case here, where you have two spin-split superconductors coupled via a spin-polarized interface. And in principle, the magnetizations in these three cases can be non-collinear, and you can study what happens to the tunneling characteristics. And then the formula becomes a bit longer, the tunneling formula. Okay, here is an example of a recent experiment. This is not the first experiment to study spin splitting, but it's just a representative one. So how you see the spin splitting in tunneling experiment is just you have the spin split gap, which is basically the distance between these two peaks is twice the induced exchange field. In this case, we have two superconductors. But I think in this experiment, actually, the exchange field was present only in one of them. Okay, if you magnetize this sample. So in this first case, they were not magnetized. The magnetic domains were random. So the peaks were kind of equal height. But if you magnetize the system, you start to see the effects of spin polarized tunneling, where the tunneling probability through the system is different for spin up than spin down particles. And in this case, these peaks sort of reveal the spin polarization of the conductance. Actually, the peak heights are proportional to it. In the general non-collinear arrangement of these systems, if the two magnetizations in these cases would be non-collinear, you actually would get in total 8 peaks instead of these 4 peaks in here. Now, it's important actually that this experiment, what was used was aluminum. It's a light element, and in a light element, the spin-orbit interaction is weak. And in this case, you can see these peaks. You can resolve them sort of easily. If you would have heavier elements such as niobium, it would be much harder to see this splitting because of strong spin relaxation. Yeah, and I forgot to say that this erbium sulfide here is the thermatic insulator. Okay, if you have 2 superconductors, you can sort of extend this tunneling description from quasi-particles to the Josephson effect. And one interesting thing that you get from there is the so-called phi-zero effect in the general case that you described here, so that the supercurrent contains not only the sine phi part, but actually also the cosine phi part. And which means that in the equilibrium case where the supercurrent is 0, or when you don't connect this to any external circuit, then actually the equilibrium phase difference is finite. And in order to get this J2 term, you basically require non-coplanar magnetizations in this system. But this is kind of simple enough structure that you can study actually analytically. So you can get in the absence of spin relaxation, you get this all these quantities analytically. Okay, so this was the sort of easiest tunneling experiments on spin split superconductors. Now I would like to point out one point here related with the asymmetry of these peaks. So the density of states that I just showed, sort of it contained these peaks which were split by the exchange field. This picture is from the first experiments by Mercer and Tero on this effect. And another way than just describing this kind of NZ mode or the spin split mode of the density of states here is to just look at the spin resolved density of states. So spin up, due to exchange field, spin up density of states shifts to the right, and spin down density of states shifts to the left. And but the superconductor actually still knows where the 0 is, because this is the chemical potential of the superconductor. So what you see in particular, if you look at this red picture, is an example of a giant electron hole asymmetry. The black picture, which is for the right spin, contains also an electron hole asymmetric density of states, but then with an opposite direction, in such a way that the sum of these densities of states is actually completely symmetric, right, with respect to 0. But now, if you combine this with spin polarized tunneling, so if you have a finite spin polarization of tunneling, you weigh these different spin components differently, and this means that you actually have a sort of full. You can actually resolve this electron hole asymmetry, and yeah, and this is what I'm telling here, and this actually leads to a thermatic effect, and I try to describe it a bit here. So what the thermatic effect is that you have a general contact and between 2 electrodes, and then you can bias this contact either with a potential difference, a voltage, or a temperature difference here. And then these 2 biases, they drive charge current and heat current. And let's say, and then you can write the response matrix, response in terms of a matrix, which where the diagonals are the charge conductance and heat conductance of the contact, and the off-diagonal parts contain the so-called thermatic coupling effects. And then if you have a finite thermatic coupling, for example, a temperature difference driving a current, you can make a heat engine whose efficiency you can study and you can define different types of figures of merit, like this so-called ZT for this thermatic contact. Now, thermoelectricity in superconductors have been discussed since actually the 1920s. Meissner claimed that there are no thermatic effects because whatever you would have, they would be cancelled by supercurrent. This is more or less correct, but Ginsburg pointed out that actually you can see them in multiply connected structures, but they are very small. And actually, Galperin discussed them in the 1970s and showed indeed that the thermatic effects, they are finite in superconductors, but they are extremely small. So this alpha n is the normal state thermatic coefficient of metals, and then this is multiplied by a quasi-particle factor, which is below 1 in superconductors. So the main message was that superconductors are extremely poor thermoelectrics. But actually, what I'm claiming here is the opposite, that if you spin split a superconductor and you study it via tunneling, you actually get a huge thermatic effect. And here, what you only need is to have the spin polarization of tunneling and then the spin splitting of the density of states, and you get a large thermatic coefficient, and which, you can also study analytically in a certain low temperature limit. And and this was a prediction, and from 2014. And I should mention that there was before us already some work by Wolfgang Belzig's group in multi-terminal superconductor ferromagnetic junctions, who also noticed similar thermatic coupling. Anyway, so that was the prediction 2014, and this was tested by Detlef Beckmann 2016, and they indeed found a sort of very large thermatic current in an experiment. I will not go too much into detail, but basically they heated one part of one electrode with a heating current and measured the thermatic current resulting from the temperature difference. There. Okay, so in the review that I mentioned, we also analyzed the possibility of making a heat engine from such system, including all possible, let's say, heat relaxation mechanisms and so on. And what we found out was that this figure of merit can actually be very large in such systems. I believe this sort of device has not yet been realized, and it's basically it's a challenge for experimentalists to do this. Okay, but then one can also ask where to use this giant thermatic effect, and this is what we have proposed, that you can actually use it for as a detector. So thermatic effects are used at room temperature for various effects, converting waste heat to electricity, but using a superconductor for such a thing is not that feasible. But superconducting detectors are actually the best detectors of electromagnetic radiation. And what we also propose here is to use this effect as a detector, but there's one difference to the existing superconducting detectors. The existing superconducting detectors rely on measuring the temperature dependence of resistance or inductance. Here, the idea is that actually the mere temperature difference that you generate by absorbing radiation actually generates a current that you observe. So the difference is that you don't need any bias lines to your detector. So this is kind of self-powered by the radiation itself. And we are pursuing sort of making these such detectors in this SuperTED project funded by FET Open. Okay, there is another sort of suggestion where this could be used, which is scanning thermometry. I know that spin split superconductors actually have been used for probing spatially resolved spin polarization. Already there are a couple of works from a few years ago on this. And then scanning probes have been used for thermometry at room temperature. I believe these use either the temperature dependence of the resistance or also thermatic effects existing at room temperature. But now, using spin split superconductors and this thermatic effect, you could also resolve spatially temperatures without applying current at low temperatures. And this might be interesting to realize. Okay, I presented earlier a coupling between charge and heat current, but in fact you can study a bit. You can extend this response matrix a bit by not only describing charge and heat, but also spin and spin heat in here. And then you get the 4x4 matrix, which is actually full, and only depends on these basically four quantities: the conductance, thermal conductance, spin polarization, and this alpha, which describes the spin dependence of the density of states. Okay, and so this was the part on spin result electron hole asymmetry and the thermatic effects. And in the next part of my talk, I would like to sort of exploit this coupling of charge spin energy and spin energy modes in the bulk superconductor. And this actually connects to yesterday's talk by Rembert. This is one of the things that you can do in a Zoom meeting. You can copy shamelessly other people's slides. Rembert discussed yesterday in his tutorial the desire to realize a dissipationless spin conductor where the resistance that you measure, or the spin resistance, is independent of the length. And he compared this to the case of superconductors coupled to two leads. Indeed, in this case, in a long superconductor, the resistance is independent of the length. However, there is still a surface effect related with the conversion of the quasi-particle currents to supercurrent. And actually, I'm going to next talk about this conversion. And sort of the experiments where this conversion are best studied are these similar non-local experiments as were discussed also in two talks yesterday, where you have a metal, aluminum in this case, coupled to electrodes, and then you drive currents from this sort of injector electrodes, and you study the currents in detector electrodes. And if this aluminum is in the normal state, and if the injectors would be non-magnetic, then the detector current would be simply zero due to charge conservation. However, Clark and Tinkham showed in the 1970s that if you take the superconductor, I mean, if you take the metal to the superconducting state, such an experiment can probe a charge imbalance in superconductors. And charge imbalance basically means that the quasi-particle potential is different from the condensate potential. And even though there is charge neutrality, such a quasi-particle potential can actually decay because once the quasi-particles are sort of connected with the condensate, basically they are transferred to Hooker pairs. And this decay is usually via inelastic collisions. Now, a similar sort of setting was discussed in the context of spintronics by Johnson and Silsby in the 1980s. And we heard yesterday also examples of this case where you can study the spin accumulation in this system, which can decay via spin relaxation. And then now if you place these contacts at multiple locations, you can also study measure the spin relaxation length in this experiment. Now, actually, this experiment that I show here was designed to study the first spin injection into a superconductor. But to understand this experiment, we actually needed to extend the description of charge and spin imbalances a little bit, and this I will discuss next. So, and basically the concept is about sort of what happens to quasiparticles once you sort of inject them and you sort of occupy these spin split number energies in different ways. So the question is, what are the different ways to actually occupy them? So the first way is that of the charge imbalance, where you put more quasiparticles to the electron branch than the hole branch. Then you can have also spin imbalance, where you put more electrons to the let's say one of the spin bands, in this case down, than the spin up part. You can also have spin energy mode, where you put more electrons on spin down bands and more holes on spin up bands. And then you can have the energy mode, where you just simply put more to all parts. Now, okay, and this is sort of the description here is basically that the distribution function that goes into the Keldysh-Green's function is now contains terms that are Nambu or spin matrices. This is the formal description of these non-equilibrium modes. You can actually also then couple this to the self-consistency equation, and you get now sort of corrections to the delta. So the FL is the energy mode, and this is hyperbolic tangent in equilibrium, and this is what you get in the equilibrium part. But then you actually get also non-equilibrium corrections due to these non-equilibrium modes and the presence of this sort of spin triplet pairing. And now the description also in this case actually starts from the Husserl equation, but now for the Keldysh part of this Husserl-Green's function. And and basically the physics is that of describing the kinetic equation, so the Boltzmann equation for superconductors. And what I include here is now the diffusion term from the Husserl equation, and then different spin relaxation terms. And then one can, in principle, also describe collision integrals for inelastic scattering. And what you get is a kinetic equation, which looks typically like this: that you have some gradient of the currents is equal to some term times the distribution functions. So the right-hand side describes relaxation, and the left-hand side describes the currents. And this is I'm describing only the stationary case, so there are no time derivatives in this case. And the type of relaxation that you get is in this description is that of spin relaxation, but also these R terms here describe actually a coupling to the superconducting condensate. So they relaxed eventually some quasiparticles to the Cooper pairs. Now the physics is inside the sort of the way how we write this current. So if we would have a normal model, the different modes, non-equilibrium modes, would not mix, and basically we could just write these currents in terms of the gradient of the corresponding distribution function. And in this case, we can actually also integrate this over energy and get, for example, the spin diffusion equation that was discussed by Rembert yesterday. So this spin diffusion equation comes from actually it's not FT, but it should be the FT3 mode here. So this is the spin mode. Okay, if you study this in a superconductor, the first thing that you get is that the spectral coefficients that called the diffusion, they actually become energy dependent. And you cannot do this energy integral trick anymore, so you have to do it first sort of energy resolved. And you get basically two spectral diffusion constants, dL and dt, describing separately energy and charge transport. And if, for example, the energy transport dL is quite simple. In this case, it's basically a step function. Here it's a little bit broadened step function. And this basically just tells that below the gap, there is no energy transport in a superconductor because you cannot have entropy transport inside the gap. And this describes then the poor energy transport in superconductors. Now, you can also actually add a supercurrent. So if you have phase gradients in the order parameter, you can add supercurrent terms here, and this fills up a little bit of this matrix. So in this case, for example, it couples the FL and FT modes, which is a coupling between charge and heat mode. And this describes a certain supercurrent-driven thermatic conversion between temperature gradient and charge imbalance. This was already actually found in the end of 1970s. Now, if you have spin split superconductor, you can guess that this matrix fills up. And actually, you couple all the different modes. So you get, yeah, there should be a gradient actually here. Apparently, I'm missing some gradients, but yeah. So you get diffusion that couples the energy and spin modes and charge and spin energy modes together. And then actually, you can also have a possibility of spectral spin supercurrent that couples the rest of the times. And let's say already without the supercurrent, the fact that the energy and spin mode are coupled actually explains experiments that I mentioned before by the Kasrak group, who found out that the spin transport in superconductors seemed to have a very long range. And the long range was explained by the fact that the energy mode actually decays only via inelastic scattering, which is weak at low temperatures. Okay, so far I have discussed superconductors and the superconducting dynamics by assuming that the magnetism is completely static. But next I kind of lift this assumption and discuss a bit magnetization dynamics. And then yeah, and the setting is the following. So, or maybe actually I should mention one thing here, is that in order to sort of solve these kinetic equations, for example, in this setup here, so you solve them inside these wires, but you also need the boundary condition coupling these electrodes that couple to the wire. This boundary condition is actually given by the tunneling that, in the case of tunneling contacts, that I described already earlier. Now, if you have dynamic magnetization, you can also sort of drive other things than what you would have via simply charge current in this case. And this, in particular, you can drive spin currents. Okay. So the case of dynamic magnetization is the following. You have two magnets. You have in one of them the magnetization can precess around some field, and this precession actually pumps spin into the other ferromagnet. Or if you apply a current through the system, this current applies a spin torque onto this magnetization precession. And these two processes are on-cycle reciprocals of each other. Here, my idea is to study what happens to this magnetization dynamics once you couple from this dynamic magnets, you couple this to a superconductor containing a spin-splitting field. And okay, The description of the dynamic magnetization is that of the Landau-Lifshitz-Gilbert equation, where you basically study the dynamics of the magnetization vector, assuming that actually only the vector direction can change in the dynamics, and let's say Landau-Lifshitz equation is the one where which contains this first term, which describes the precession due to an effective magnetic field. This term here is the Gilbert damping term, which then damps this precession, and then the last term was added by Slonczewski, and it describes the spin transit torque from a spin current from an adjacent magnet, and it can describe either sort of actually there is a field-like torque and a damping-like torque that you can get from this. And yeah, and as I already mentioned, there are sort of two phenomena which are reciprocals of each other. So a spin current drives actually a non-collinear spin current to the magnetization direction drives the torque, that drives the magnetization precession, and then the magnetization precession itself actually pumps spin current into an adjacent metal, and this pumped spin current actually also acts as a damping of the magnetization precession. And you can describe these as on-cycle reciprocals, as was discussed in this paper in more detail. Now, I want to study this in the case of superconductivity and sort of to enlarge the tunneling description to that case. So previously, I already shown that you have this on-cycle matrix for collinear transport, this coupling spin modes and energy modes and charge modes. And now the question is, what about the case where you have magnetization precession and general non-collinear magnetization? And this is the case of thermatic resonance. And what was shown by Cherkovniak, I believe, some 10 years ago, a bit more, is that the FMR actually shows up as a spin bias in a system where if you switch the frame that precesses with the magnetization, and then you can actually study what happens due to the spin bias. And this is what we did in this paper. And so now the on-cycle matrix looks like this in linear response. You can also look at nonlinear response, but maybe the linear response is the easiest to present. So the thermatic coupling is basically the upper part of this matrix. So you have a coupling between the temperature difference and current, for example. This depends on the magnetization angle as a cosine theta. But then now as new terms, you have actually a coupling between magnetization precession and heat current. And actually how this shows up is that a temperature difference would drive a torque, would give rise to a torque, or the magnetization precession at frequency omega would drive a spin cooling or heating, depending on the direction, on the sign of alpha. Similar kind of things were studied without spin splitting, where in this case, you need to go to the nonlinear order by Triff and Cherkovniak. And okay, one thing that you can study is the possibility of auto-precession in this system. And I guess I will not go into too much detail, but we studied possibility of, in principle, driving an auto-precession in the case of temperature difference in the system. And in principle, we found that it's in principle possible, but the problem basically is to overcome the intrinsic damping in these cases. But we found that it's not completely impossible, so it's could be done. Okay, but maybe an easier way to study the interplay between superconductivity and magnetization dynamics is that of the AC measurements, and where the idea is that you sort of send an AC signal to such a system and then study that reflected signal. And I believe Tero HEIKKILÄ will later today describe such measurements of the thermatic resonance of magnets next to superconductors. And basically what you always measure is either reflected or transmitted signal, and which typically have some resonant features, like in this case schematized here. So the interesting aspects then are the resonant frequency and the line width here, and the effects on the line width. And I believe Tero will describe the line width due to damping by spin pumping into a superconductor. I actually will mention also another mode that becomes relevant here, which is the Higgs mode. And I guess for this I have a couple of minutes still. So this work is also described a bit more in Risto Ojajärvi's post later today. But here I just try to give a glimpse of what we did. So in superconductors, they break a U1 symmetry. There are two kinds of collective modes. There are the Goldstone modes, which are basically the modes where you go along with the valley, and then there are Higgs modes which are sort of the modes in perpendicular direction. And the Higgs modes measurements have been carried out in the past, and usually measuring the Higgs mode requires a third harmonic measurement. So you apply an AC field and you study what happens at the three times the AC frequency. Now, what we basically saw here is that if you have a spin split superconductor, you actually get access to the Higgs mode already from the second harmonic, and this way you actually and what the Higgs mode actually drives is AC spin current. And now if you couple the system to via polarized spin tunneling to a ferromagnet, you can also then couple it to a AC charge current. And the details are given by Risto in his poster, but basically the idea is to get the Higgs mode from the self-consistency equation, which then solves a so-called polarization operator, and the Higgs resonance is actually the pole of this polarization operator. And here is an example of the AC spin current as a function of temperature for a fixed frequency, and it shows its Higgs resonance. Similar kind of effects were discussed by Wolfgang Belzig and others. In the case where there is no spin splitting, but there is actually a finite DC voltage, where you can also couple the Higgs to the second frequency. An alternative way actually to access the Higgs in principle is to study its coupling with the thermatic resonance, where the spin current driven by the Higgs mode is then coupled to the thermatic resonance mode. So this would show up as a peak in the Gilbert damping at the frequency of the Higgs mode. Okay, I'm coming to the end of my talk, and I hope I have given some sort of basic idea of the transport effects in spin split superconductors, how actually it's kind of natural to study spin transport in superconductors that actually contain the spin splitting field. But I have, of course, left out many interesting topics, and I just mentioned a few here. This is definitely not an exhaustive list, but I already mentioned that there would be many interesting effects from spin orbit coupling, and but it has been a bit of an issue of describing the spin orbit coupling together with superconductivity, and especially the work of Tocatli and Bergeret should be mentioned here. So in principle, in particular, what you get in these cases is this anomalous phase effect that the phi zero effect that I already mentioned, the so-called long-range triplet correlations, so the other F parts, and then also the challenge would be to describe the spin Hall effect. In terms of recent experiments, one I think interesting one is the one from Cambridge, where they studied the superconductor-mediated coupling between ferromagnets, which was actually predicted by Dejean already in the 1960s. This, I believe, will be discussed in a later talk today by Tero HEIKKILÄ, which is thermatic resonance and spin, and then actually the possibility of actually seeing spin supercurrents. This is another recent work which I believe was published maybe last week, which is an inverse spin Hall effect into a superconductor, which would then require actually using this theory. And then I should mention the work of Marco Aprilli, where they show that they have measured actually this spin temperature in spin split superconductors. This brings me to the end of my talk, where I hope I have shown you how split superconductors actually perhaps the main interest there is the fact that they can actually couple strongly between spin, charge, and heat, and basically this shows up in studies of the dynamic magnetization. Thank you for your attention.